טוב, היום הרצאה, יש לנו, today we have a nice lecture, not so long, about materials analysis for microelectronics. And if we have time, I also prepared another lecture called metrology, which is not supposed to be, it's not in the syllabus, but I think that this lecture is, we can finish in time, so let's see. So practically, the lecture today is how do we apply, what's the philosophy of modern material analysis experiments and why it is needed for the integrated circuit industry. This is a lecture which overlaps all the topics that we studied in the semester. And because we studied lithography and wettage and CMP, chemical mechanical polishing, chemical vapor deposition, atomic layer deposition, we have all the other electroplating, diffusion. Practically, we studied a lot of processes. And I have to tell you that about 30 years ago, when you run a process in a company, you start a wafer and you do lithography, then you do the next step, and from time to time you do some metrology or some measurement. It was not so intensive. And if you want to do some characterization, you take the wafer outside of the fab, you take it out of the fab, characterize it. What happened in the last 20 or 30 years that the more complex the process, the more measurements we need, because there are more tools today which can help us in fabrication. And the production modern nano devices incorporate different process steps. And what we need is a robust process to realize in high quality devices. Robust process means the day in, day out, and you always have variations in manufacturing, day in, day out, everything is working, everything is in spec. And the most important is that the yield of the process is as high as possible, which means definitely above 90%. It's sometimes much higher. So we need some control on the process, and you can do the control in situ, which means during the process on the process wafer, or you can do it outside, taking some samples out. Now, taking samples out is expensive, so you want to, as much as possible, to do on the wafers itself. So you need some feedback. Besides, multi-techniques analytical approach needs to be employed in order to examine the possible mass process mechanism. Now, what does it mean? It means that, let's say, for example, I'm growing gate oxide. And the gate oxide has to be 6 nanometer, the composition has to be hafnium oxide, and the surface properties to be such and such. So I want to take the wafer, and during the process, to measure, to verify that the oxide thickness is uniform all over the wafer. I want to measure the electrical properties. Or if I deposit materials, I want to make sure that I deposit the right materials. Now, uniformity is a very big issue, but we'll talk about it later. So basically, 3 main types of lab works are needed, which are process characterization, failure analysis, and research and development. All this become more and more popular in manufacturing. So let's jump into the water and discuss what does it mean, material analysis properties. If you think about it, a common scheme of modern material analysis experiment, we take the sample, we apply some light, electrons, ions, we put some energy in, we measure energy out, and we trust the law of conservation of energy, which means the total energy is, if we have a molecule, for example, inside, we have rotational, vibrational, and translational energy, and we have, and typically, the rotational energy is less than the vibration energy and less than the electrostatic energy. So practically, if we apply some source, common scheme of modern is apply some energy, and since most of the process is on the wafer, it's practically surface analysis. And we can apply a wide range of photons. We can illuminate it, We can illuminate it by X-ray photons, by ultraviolet photons, visible photons, and infrared photons. And each one of them can generate emission in the visible, in the X-ray. I can illuminate, I can apply electrons and measure X-ray emitted. And there are many possibilities, but the main role is that I can apply ions, photons, electrons. This is the source. And I can measure ions, photons, and electrons. And all this can be used to characterize the surface. So what's on the list? This is kind of a grocery list. What we can do. If we apply ions and measure the target ion, this is called SIM, secondary ion mass spectroscopy. I shoot ions, ions are being sputtered, I measure what is being sputtered. So if I take SiO2 and I shoot argon ions, the argon ions break the silicon dioxide and I get silicon out and oxygen out. So I can measure the composition, and since I can do etching during the measurement, so I can actually get the profile of the material. I can get the profile of the dopants or the materials or the composition, if it's an alloy, as a function of distance. I can apply ions and measure electrons which are emitted because of the collision. This is in a process called focused ion beam. I take a focused ion beam, which is a focused ion beam. This is what the name says. And the beam hits the silicon, and because I can transfer energy to the electron, some are being emitted. So I can get, for example, I can take the silicon, the ion beam, and scan the wafer and look at the scattered electron, and actually generate a map, an image of the surface based on electron emitted due to interaction with ions. It's similar to electron microscopy, but in electron microscopy we use electrons to generate secondary electrons. But I can also use ions to generate secondary electron, and this is a different kind of image, which is, by the way, very sensitive to grain boundaries, and it's very nice to look at crystalline structure. I can apply ions and practically measure the mass, which is called inductively coupled plasma mass spectroscopy. I apply energy to the system, generate plasma, and look at the emission and measure the mass of the plasma. I can apply electrons and generate secondary electrons, and this is called scanning electron microscopy, or dual beam FIB, which is a focused ion beam, where I use the ion beam to cut the sample and the electron beam to image the sample. Or I can take electron, and the electron hits the sample, and because of Rutherford interaction, some of them can be backscattered. Backscattered. This is also scanning electron microscope. So this is secondary electrons. I can use transmittance, and this is scanning transmission electron microscopy or transmission electron microscopy. I can, when I illuminate with electrons, illuminate is metaphorically, when I take electrons and I shoot them on the surface, I can generate X-ray. And the X-ray is proportional to the mass of the atoms of the target. And we know that heavier atom emitted X-ray in different wavelengths, and the wavelengths depends on the mass of the atom. So this is called energy dispersion X-ray spectroscopy, which is very useful to measure composition of samples. I can use X-ray, and I have used X-ray fluorescence. Can be regular XRF or TXRF. TXRF is when I shoot the X-ray in a very shallow angle. No, I don't want to change. Dismiss. V or visible. Atomic force microscopy. I can use laser pulse, like in the Raman spectroscopy. I don't know if you studied the Raman interaction, but I look at, in this way, I look at the interaction of the light with the vibration, with the modes of vibration in molecules, so I can actually look at chemical composition of the surface. Or look at the infrared, I illuminate with infrared and measure infrared. And then this is called infrared spectroscopy. And the most common tool is a Fourier transform infrared spectroscopy. All these are available in the fab. So now let's divide the whole method that we have. Let's put this side. This is morphology. This is composition. All these methods, you can measure composition and the properties of the surface, but you can also measure the morphology and the topography. Now, some of the methods can measure both. And in this class, we related all techniques from microelectronics industry perspective. This is slightly different in comparison to academic research because the way we evaluate the method is the ease of use, is it upgradable, time to data, and meeting the technology needs. This is what we need. And this is atomic force microscopy. We are going TEM-STEM, secondary ion electron microscopy, focused ion beam, FTIR, Fourier transform, infrared, Raman, secondary ion mass spectroscopy. All this we are going to study in this lecture today. It's kind of a long list, but I'll try to every method to give you the highlight. You're not going to be expert in any method today, but you will see the highlight and how it's being used in manufacturing. So let's look at AFM. This is the one on the leftmost on my list, and this is used to measure morphology. AFM, atomic force microscopy. It's a real space imaging technique for producing high-resolution topographic images of a surface, insulators, semiconductors, and conductors. It's a relatively new technique. When I was a student, it did not exist, but in the last 20 years, it became a dominant technology because you can measure pitch, height, depth, angles, and roughness of the surface in the nanometer scale. Can be combined with atomic force profiling, capable that extends scan size up to 5 centimeters, keeping sub-angstrom resolution in height. You can do it on any sample. The preparation is it's trivial, just has to be clean. Operates in air, and it depends on, I'll show you how it works. It has a tip, the tip scanning the surface, so it depends, the result depends on the tip shape. It does not provide information on chemical content, may be time consuming. It's a relatively slow system, but relatively, everything is relative. So practically, how it works. This is your sample. You take a needle, and the needle, you try to take the needle and to move it toward the surface. And if you remember from your classes at material science, introduction to material science, if you take a material and try to bring it close to another material, practically there is a point. Initially, you may have some attraction forces between the molecules, but after you reach a certain point, you start to have a repulsion forces. So this is what they call the Lennard-John potential, that you say that initially, as you're getting closer, you may have some attraction forces. And if you're getting too close, so this is the potential. If you take one metal, move it closer to the surface, you may have some, this is material A, this is material B. You may have some overlap of electronic orbitals or van der Waals forces, and you can have some attraction between the two materials. So initially, as you get closer, at infinity, the potential is 0. As you're getting closer, in many situations, the energy is lower. But as you're getting too close, then the potential starts to go to the opposite direction, which means you simply the two materials kind of hit each other, and there is a strong repulsion forces. But if you do the analysis, typical force is like A divided by r to the power of 13 and B over r to the 7. This is the force. The potential is actually 1 over r to the 12 minus r, another constant r to the 6. So practically this is, you have a minimum here, and here the potential cross 0, which means from the minimum here you start to have repulsion, here you have attraction, and this is like the optimum place. So AFM uses a very small, sharp, about 10 nanometer tip at one end of a flexible cantilever. This is a cantilever, held very close to the sample surface. And practically the tip is rastering. There's a raster scan across the surface while oscillating in the resonant frequency. This is what we call the tapping mode, that we are not, the tip is not just constantly moving, the tip is resonating and moving very close to the equilibrium potential. And from this kind of mode, the topographic image generated from feedback on RMS amplitude. What does it mean? It means when the tip is getting closer, you get some repulsion. Getting faster, you get some attraction. So there is some average force between the surface and your needle. And the surface is going, when you raster scan the surface, the distance may change. So the new equilibrium point will be different. So what you're doing, you take a feedback mechanism to keep the force relatively constant. So what happens if the force is relatively constant, practically your needle is gliding in a certain distance over the surface. You can work in a contact mode, where you're really touching the surface, or in a non-contact mode. You can oscillate or non-oscillate. And the topographic image generated from the feedback at the cantilever, deflections of the cantilever are feedback to the tip. And this is what you usually get. This is AFM sample. This is AFM line scan showing, this is tungsten plug rhesus profile. This is a low resolution. This is high resolution. This is a tungsten plug. This is, you can take a line scan, and this is what you get in a line scan. Or this is a copper aluminum polycrystalline layer. When you scan it, and what you do, those are artificial colors. This is not a real color because you have a tip and the tip is scanning. But you can translate the various height to a different color, and this is how it looks in artificial color, and you can easily identify grain boundaries and even some twins in there. This is probably twins, I'm not sure, but definitely you can see the grains on the structure. So the signal in is tip detection, signal out is the feedback signal. Typical resolution is 2 to 5 nanometer. The height resolution can be as low as 1 angstrom. Today you can even go to 300 millimeter wafer, so very large scan. Sample preparation is minimal. You can go 5 to 6 micron in Z, 70 to nanometer in X and Y. This is the total range. Time is typically a few minutes, 10, 20, 30 minutes per image, so it's slow. You can work on pattern wafers, you can work on blanket wafers, and other applications, subsurface electrical defects. I'm going to show you next how you can use this to measure potential. So, and there's other mode to operate it, which I'm going to show in a minute. Calibration reference, usually you take a NIST, National Institute of Standard Technologies, you take a standard wafer, calibrate it, and it's okay. And sensitivity is very small. I didn't put a number here. So practically, you can take, there are a few modes. You can take the tip and do amplitude modulation, which means you modulate the amplitude. Or, so what you see, this is a modulation, and when this is a step, this is like, let's say this is the surface, you have an edge here, and you go up to here. So here, this is the modulation of the output, the amplitude change you have here, and then you have an amplitude change. And you keep the frequency of modulation. Now, why we are doing it? Because you can actually work without modulation. But when you do modulation, it's easier to follow the signal using AC locking amplifiers and AC locking mechanism. And you're actually looking for the average. You can identify the average motion, and you can identify the amplitude of the motion. You can also do frequency modulation. In this case, this is like a set point, and when you are modulating the frequency, and as you go over a step, you see a frequency change, and the amplitude is fixed here. So both AM and FM modes maintain contact tip sample separation. AM mode uses oscillation amplitude changes as the feedback, while in FM mode uses the frequency change as the feedback. What you're doing, you're scanning and you are vibrating, and you can, feedback means you want to maintain a constant frequency or you want to maintain a constant amplitude. So whenever there is a change in amplitude, you apply a feedback, and your signal is the feedback, how to maintain the fixed signal. So if you look for the people here from electronic engineering here, you practically, how do you measure the motion? One easy way to measure the motion up and down is you illuminate, you take a light, and the light is being reflected from the tip, and you put here a sensor, and the sensor is a 4-quadrant sensor, which means if you hit the sensor, this is a photodiode, and this photodiode has 1, 2, 3, 4 quadrants. And every quadrant is a photodiode. So if the light is in the center, all the diodes have the same signal. But if the light is going from here to the center to here, this photodiode generates a larger signal, and this photodiode a lower signal. So by using this method, you can identify the motion of the tip, and you translate it to a signal through the preamplifier. Then you take the signal out, and you apply a feedback signal that you want to maintain it on the same place. You want to maintain it same place means same force, which means the same distance. Now, this is a very simple principle. You apply a tip, and if it's going up and going down, you try to maintain a fixed force between the surface and the tip. But you can also use this technique to look at Fermi level, look at charge. You can use it to measure change in potential. So electronic, if you are thinking about the tip as a material and the sample as a material, this is the tip, this is the sample, and if you can, this is a solid, this is a solid. So you can look at the electronic level of the sample and the AFM tip for 3 cases. First one, tip and sample are separated by distance d with no electrical contact. Then what you do the next step, you are connecting them. The tip and sample are in electrical contact. There's some, and because they have different Fermi level, what happens if you apply, if you connect them, they want to reach equilibrium, and what happens, because they have a very different level, the charge will go from the material, from electrons will go from, oops, sorry, the mouse, okay. If this is the Fermi level in the substrate, this is a Fermi level in the tip, and here, once you equilibrate them, both tip and substrate will have the same Fermi level, so electrons will go from here to here. So what you generate is you generate a potential difference. We call it CPD. And this VCPD, if you remember in semiconductor, we used to call it VMS, a metal semiconductor, but in this case, these are 2 different materials, so there is a built-in potential between them. which depends on the difference between the two Fermi levels. And if you apply a bias, for example, you put a negative bias, you can change the Fermi level here. Remember, negative bias, Fermi level going up, positive bias, Fermi level going down. So you can, external bias VDC is applied between tip and sample to nullify the CPD and therefore the tip sample electrical force. So by applying a voltage, I can, for example, nullify the potential difference, and I can use this effect. I mean, in the previous AFM system that I showed you, I have a force, I just measure the force, but I can apply a bias between them. And this is the key to another tool which is called Kelvin probe AFM. And the Kelvin probe AFM, they measure the contact potential difference, CPD. The CPD is contact potential difference between the conducting AFM and the sample. The CPD, or we also call it VCPD, between the tip and the sample, is the difference in potential. I just defined it by Q because I want the potential to be in volts, and this one I took in joules. So this is just notation. And then you can say, okay, this is good enough. But then we apply here a trick. We are actually applying, what is possible in this method, we apply an AC voltage. It's not only that we are vibrating the tip or applying force on the tip, we also apply voltage to the tip. And in the Kelvin probe, we can oscillate this signal. And we apply a AC signal and a DC signal. And what happens, using this technique, you can measure the work function of the sample. And KPFA measures the work function of the sample. Okay, the sample, sorry. Now, VAC, because we apply a AC voltage, we are generating a force, because this is like a capacitor with a string. So when we know the force between the plates depends on the charge. So the AC voltage is generating the oscillations. Now, because it's generating the oscillations, I'm changing the capacitance, because the capacitance depends on the thickness of the distance between the plates of the capacitor. So VAC generates oscillating electrical forces between the AFM tips and sample surface, and VDC nullifies the oscillating electrical forces that originate from the CPD between the tip and the sample. The electrostatic force between the AFM tip and the sample is given by the derivative of the potential. We know that force is minus d potential over dz. Potential is c delta v squared, so I got here this. Now remember, this is an approximation. I neglect second order effect. So it's practically, if potential is c delta v squared, so the derivative is delta v squared n times this. So using this approximation, if the tip potential is VDC plus VAC times sinus omega t, so delta V is Vt plus minus VCPD. I write this not here. And then I calculate the force, half dc over dz times this term. So if I look at this term, it actually it contains three terms. One's a dc term. Second, a term that depends on the frequency omega. And the third term, which actually depends on 2 omega. So if you're an electrical engineer, it's very easy to measure three of them separately. To measure the DC voltage, I take the signal and pass it through a low-pass filter. And to measure the force at the frequency omega or the frequency 2 omega, I'm using a phase lock loop or a system called lock-in amplifier. A lock-in amplifier is an amplifier that I can use it to measure the signal at the frequency omega, at the frequency 2 omega. So I can actually measure each one of the three components separately. So this one, it's a static deflection of the tip. Now, since I know VDC, which will allow me to calculate VCPD, and practically, when VDC minus VCPD equal to 0, this force is equal to 0. So when the force is equal to 0, the VDC that for this specific force will give me, I can measure the potential difference. So I can actually map the potential difference of my wafer. So if I have a silicon, and next to it silicon dioxide, next to it a piece of dust, I can actually see, not mapping the topography, but I can map the potential of the surface. The second component, it can be also used to measure VCPD, because when this force is equal to 0, also this component equal to 0. And this one, at the frequency of 2W, I can use it to do the capacitance microscopy. I know this is fixed. I can measure dC over dZ. So I can use it to get a map of the capacitance if I need. This is kind of the system, and this kind of a probe. I take I shine a laser on the sensor, and here I can use a system called lock-in amplifier to measure the signals at a frequency W or twice the frequency. But forget the specific. Let me give you an example. This is a KPFM measurement of a junction. It's very difficult to make the sample here. Imagine this is a silicon wafer that on top of it we put here a mask, and this area, we implanted all over the surface, and here we put a mask, which means only ion were implanted here. And then the next step was to anneal the sample. Now, how do you measure a profile of ions? One way to do it, I'm going to show you later, is maybe we can put it in microscope. But when I use a regular microscope, it's very difficult because here we have iron and silicon, here we have iron and silicon. And the amount of ions is much, much less than the concentration of silicon. So it's very difficult in a microscope. I can see maybe the defects, but it's very difficult to see the junction. But then I remember what I studied in semiconductor devices, that the Fermi level depends on the potential, on the concentration of the ions. The more ions, this one is boron doped. This is P plus N. So this is boron doped. This is phosphorus. So what happens here? We have more boron, less, and here we are no more borons. Here this is so here the Fermi level is below the center of the band gap, and here the Fermi level is above. So between here and here, we have almost, if the whole band gap is 1.1 electron volt, I will have like maybe 0.6, 0.8 difference. So what I'm doing, if I take this wafer and cut it, and to cut a wafer is an art by itself, how to cut it without causing damage, but it can be done. And then I scan it with the tip and measure the surface potential. And this is lateral and depth profile was measured by KPFM, and the depth profile from the measured, this is a sheet resistance. Another way to measure the profile is to measure the resistance of the junction, then etch a little bit. Measure the resistance and etch, measure, etch, measure, etch. And from the resistance, we know the integral number of ions. And then I take the derivative and I find the profiles. So this is a KPFM profile. This is a sheet resistant profile. And you can start to argue which one is more accurate, what is the difference, etc., etc. Now, this is a very nice measurement, very useful, but takes a lot of time. So this is about AFM. Now, if I also want to get very high resolution and to study morphology, but also study a little bit composition, the other method is TEM. TEM, transmission electron microscopy. What you do, you take your sample, you thin it down to become like 200 nanometers and even less. Then you put it in very high vacuum, and you take electrons with very high energy, can be 200 kilo electron volt or 300 kilo electron volt. They go through your wafer or your sample, and the beam is sufficient energy to propagate through the specimen due to several contrast mechanisms associated with interaction between electrons and material. The transmitted electrons form an image. So the main use is microstructure and atomic structure. You can get today TEM with subatomic resolution. You can see atoms. You can see molecules. It allows identification of different phases in solid, etc. Sample preparation is very complicated. You need to thin down. It's very time consuming. The data incorporating is not straightforward. Because you take, this is your sample, you shoot electrons, they go through your sample. So there's some interaction in between. The interaction is not necessarily straightforward. You have to really understand it and analyze it. Also, if there are some magnetic forces, they can shift the trajectory of your atoms. So analyzing the image is not trivial. And it looks like this. This is an electron gun. It's how do you generate electrons? You take metal, we heat the metal, use filament. The filament is being heated, and the electrons are extracted. And typical electrodes today are what we call field emission guns. Field emission guns, in the good old days, people used just heating. You take a tip of tungsten, you heat it, electrons are being emitted, and you collect the electrons. The problem is this method that the electrons may vary in energy because you have temperature. And very high temperature, there are some fluctuations. So the energy, the electrons were not so, I mean, it was quite monochromatic, but you can do much better if you take a tip and apply very strong electric field and you extract the electrons by using field emission, which means applying a very strong electric field which simply pulls out the electrons from the material. The electrons are going actually by tunneling through the barrier on the surface, and because you can do it at a low temperature, relatively low, all the electrons have the same energy. The beam is much more monochromatic. And then the beam is going through the chamber in vacuum. And you have a lens. And the lens are focusing. Everything is in vacuum. And the sample are going through. This is the sample holder. The beam is going through a sample, and you get the image on some screen. You can have various types of screens. And there are few ways to operate this machine. The standard TEM, the BF-TEM, the standard TEM imaging with mixing of the mass thickness and diffraction contrast. You can have because when your electrons go through your sample, if your sample has some periodicity or has some crystalline structure, you can get some diffraction. So you can have the bright field TEM, BF, which means you look at the electrons which are passing through your sample. So denser material will be darker, less dense will be lighter. But some of your electrons are going, and you have some diffraction. And instead of looking at the main beam, you can look at the diffracted electrons. And this is diffracted. This is the dark field TEM. You look at the electrons which are on the dark field around. It's almost pure diffraction contrast, very useful for detecting crystalline materials and their orientation. Now, machines which are very accurate, which are the expensive machine, we also call them high resolution TEM, which you can go to atomic level imaging for ultra thin layers. And sometimes, instead of looking at the whole beam, you just point at a single point and you look at the diffraction of the beam. This is very specific measurement. Let's say you look at some metal and you want to know at this specific point what is it made of. So you shoot the electron beam on this specific point and you look at the diffraction. And for every crystalline material, you have like a fingerprint, a different diffraction. So this is called selective area electron diffraction, or SAED. which allows you to look at diffraction pattern from specific points. And in order to do the analysis, you need to get some good reference, because every material will have a different, or not every material, even different phases will have different diffraction patterns. And you can analyze the phase structure, you can analyze their orientation. And then you have convergence beam diffraction. It's very useful for strain analysis, because the material properties depends on its composition and structure, but also depends if I apply force on it. So you can look at strain inside the structure. So all these are various modes to operate a TEM. Now the basic contrast mechanism, let's say I shoot the beam. This is incident beam, and I have a periodic structure. So what happens, I will have like the direct beam reflection, but I also have a diffracted beam. And between them I have certain angle. So this is diffraction contrast mechanisms. Now this can be in a, this is like a one-dimensional, this can be a two-dimensional. So if I have the diffraction, this is one plane, this is another plane, and each one will have a different diffraction, I will get some diffraction pattern. Depends on the orientation and various. Since you're not most of you are not crystallographers, it's very difficult. I don't want to go too deep, but imagine, for example, that you drive in a car and you go by a grove. If you look at the crystal or you look at the grove of oranges, as you drive, you see different directions of different like crystalline structures. So if you look at the very complex three-dimensional structures, the periodicity depends on the X, Y, and Z, on if this is FCC, BCC, Wurtzite. Every crystal will have its own specific planes, and each one will have a different diffraction pattern. So this is now you can also have the interaction between the electrons and the nuclei. Imagine this is a nuclei. Let's say it's positively charged. So what happens, and you shoot an electron, the electron can just go around, and this is called back-scattered electron. And you can actually have, it's actually, this is not a strong signal, but you can have some of the electrons are not going through the sample, but just going and returning. This is called back-scattered electrons. And you have electrons which are going forward, like scattered electrons, because electrons can interact with the materials. So all these are factors that practically make the beam, instead of going straight, they can go in a different direction, which means this affects the image. Now you also have a mass contrast mechanism. This is the incident electron beam. And let's say I put here material, gray material, which is a low mass material, let's say aluminum or boron or a light atomic mass. And here I put an atom, a mask with a high atomic material, higher mass, like tungsten, gold. So what happens if I shoot here the electrons? Here I will have because this is a lighter mass, the diffraction or the deviation from the straight line will be smaller because the interaction is weaker. While on the heavy material, I will have much more interactions. So then I take this structure and I put here through a pupil and I collect the information here. So what I find out that the image here first will record the morphology, because the diffraction from the amount of electrons or their diffraction from here will be different from here. Second, the amount of electrons which are being emitted from the heavier atom, or this deviation from the straight line will be different. So I can build here an image. This is like image plane. the image plane, the amount of electrons arriving here, 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 and here will be a function of the thickness of the material and the atomic weight. So I can generate here an image which is related to the atomic mass and the topography. And you have to be very careful because sometimes it's, you can, like a thick, light material may have a different or will be similar to a thin, heavy mass material. So the high resolution available in TEM is possible due to the two main factors. First, electron wavelength, which depends on the acceleration voltage. In case, for example, 200 kilovolt, the wavelength is 2.5 pm. Lambda is can given by this equation. And by the way, you have to, in this kind of energy, you have to take into consideration relativistic equations because the speed of the electrons is getting closer to the speed of light. So you need, not so close, but close enough that you need to take into consideration relativistic equation. By the way, you have to remember that the energy that some people make this, if you ask what is the wavelength of the electron, people remember that for photons, h ni equal energy, or hc over lambda is equal to energy. But if you apply energy to electrons, you accelerate them, if you want to calculate lambda, you have to take into consideration the relativistic equation. Basically, basic quantum mechanics. So this is how it looks. This is nice images of TEM. What is this here? This is tantalum on tantalum nitride. This is copper on oxide. This is, by the way, a very common barrier. The total thickness is 25 nanometer. This is measurement of TNT. Oh, tantalum TNT, tantalum nitride. Okay, this is the sense of humor of the person. But this is, by the way, very typical structure in copper metallization. You don't want to put copper directly on oxide, so you put a barrier layer. And tantalum nitride is one of the best barriers that is known, or all the best which is known. But if you want it to stick nice to the copper, you have to put in very thin layer of tantalum on top of it. So tantalum nitride is one of the most common barriers today. The only problem with this technology today, you see this is 25 nanometers. So this is good for 65 nanometer, 35 nanometer technology. If you want to go below 25 nanometer technology, you cannot make the barriers so thick. This has to be less than, total should be less than 10. What do we have here? This is high resolution TEM of gate oxide and poly. So this is the silicon, this is the polysilicon, and this is the gate oxide. And you can see this is amorphous material. And you can see here, this is atomic resolution imaging. And this is a bright field TEM image of a flash memory cell. This is, I have to guess what it is. But what you see here the trench, the contact. And you see, by the way, it's very nice here. You see that they had, whoever did this technology had some problems in filling. You look very carefully, but do you see the seam here in the center of the via? Do you see it here? This is the metal, and as you can see here, sorry, this is polysilicon, sorry. So this is a isolation between two transistors, and what they filled it with poly, and you see that there's a little void here in the center. But these are, you can see the high resolution imaging of the TEM. So TEM, the signal in an electron, the output is transmitted electrons. Resolution is in the range of 1 angstrom. Depth resolution is very high. Sample size is, we can do up to 20 micron sample. This is, you have to be careful because TEM you cannot do the whole wafer. If you want to go to do it in another place on the wafer, you have to move the wafer. But the total field you can look is 10, 20 microns. Sample preparation takes a lot of time. Useful range, basically, okay. Resolution of the system. Analysis time takes a lot of time. You can do on both pattern and blanket. Other application, ultra thin film analysis, defects, selective area electron diffraction. Calibration reference, by the way, you don't need, because you can use the silicon itself as a reference, because this is atomic level, atomic resolution system. So just look at the silicon, and we know the distance between the atoms of silicon. So if you want to calibrate it, you use the substrate as calibration. It's very sensitive. There's another, I want to steal a few more minutes from the break. There's another mode of operating the system. It's called STEM. The beam is converged to very small spot, convert to very small spot, similar to SEM, and scan across the wafer. And here, we practically can put a detector here, or a detector here. And I can, this is the high end, this is the, no, this mouse. Basically, the STEM detector is inserted above the viewing screen and forms the image in SEM. By collecting the information from the different radial zones, we'll receive a different contrast. So we have the high AADF, this is the dark field, this is called dark field. So we can collect the high angle diffraction, the lower angle diffraction. This is called bright field, the center beam. If you think about this diffraction, this is the 0 order, 1st order, 2nd order of diffraction. So you can collect various orders of diffraction. This is the high angle, the regular, or the bright field, and you can synthesize an image out of this information. So this is a high ADF, from the collecting the high angle stem of a transistor. This is a transistor. This is the polysilicon silicide source drain and the contact. And this is the stem image of a short between metal lines. This is a metal line. This is copper metallization. This is the barrier. And why the barrier is lighter than the copper? Because this is tantalum nitride, and tantalum is much higher atomic weight than the copper. So this looks lighter. And by the way, you can see here the step coverage. This was done probably by sputtering, so it's thin, it's thick here on the side walls. It's thinner because the atoms during deposition came from top. And this is a nice short, do some, probably by copper diffusion from here to here on the surface under, this is the insulator, so this is a metal failure. So this is STEM summary, and I think we'll take scanning electron microscopy, which I assume that many of you used it or are going to use it or are using it now. SEM is a primary high magnification imaging tool for close physical inspection. This is like the workhorse of the industry, capable of working with tool parts and non-wafer samples, can work with resist and wafer level. In this system, we are using electrons and their interaction with the surface. It can get very high resolution, about 15 angstrom, like 1.5 nanometer. Resolution of the electric materials is a little less. It's about 50 angstrom. And we can also do some thickness measurement with this method. It's difficult to analyze non-conducting and organic materials because they are non-conducting. So when you shoot electrons on non-conducting material, we can charge it. If we charge it, suddenly the surface becomes negatively charged and it repels the electrons, so the measurement will start to, the image will start to become dark and fade. Some electron beam damage, and resolution and contrast are sample dependent. You have to remember, in scanning electron microscopy, the image is in response to the electrons. sometimes it looks so much like a real image, so people look at it as an image, but it's not an optical image. This is an electron image, which means it's a representation of the surface. So for example, it can look like this. And this is a typical machine. This is the magnification. This is the resolution. And another advantage of this machine is excellent depth of focus. Excellent. So sometimes we even use SCM even for low resolution applications. For example, in MEMS technology, micro electromechanical systems, it's very common to use SEM for imaging because of the very large depth of focus. You can have a sub-micron resolution in the image, and you can have like 10, 20 microns focus, depth of focus, which is impossible in optical microscopes. So relatively also it's easy to use it. So if you look at this material, what do you know? That here we have a lot of scattered electron. Here we have, in the black area, we have less, but we don't know exactly why. It may be because it's a trench, maybe because it's a different material, maybe it's the same material but with a slightly different orientation. So when you are looking at SCM image, look at it with a grain of salt. It's not always what you see is trivial. So what do you have in X-ray? You have an electron gun, and you don't make X-rays, use electron directly in this electron gun. Now the wavelengths, by the way, you have to remember that E is hc over lambda, or lambda is hc over E. This is for photons. If you want to do the calculation of lambda for electrons, you have to use you have to look at actually the momentum as the momentum P is related to K, the wave vector. And from the momentum, you can relate the momentum to the wave vector k, which is 2 pi over lambda. And if you go to basic quantum mechanics, you can calculate lambda from the momentum, and you have to calculate the momentum from the potential, because when you apply potential to electron, you have a velocity, etc., etc. So for the classical non-relativistic physics, this is lambda. But if you start to go to high V0, to high potential, when you accelerate at very high voltage, then the wavelength, this is the Planck constant, has two components. One is identical to the non-relativistic term, and the second one is the relativistic terms. And in high-resolution systems, in high voltage, you actually need this term to calculate the wavelength. So these are just equations. But how does it work? Again, you have an electron gun. The electron gun can be a thermal gun, which means you hit the metal, electrons are being emitted by thermal emission. It can be field emission gun, where you apply in this specific one, you have an anode, and the anode has a very high potential, so it extracts the electrons from the surface. We can also have a combination when we hit the gun and apply some voltage. So if you have a voltage between, this is positive, this is negative, electrons are attracted. And some of them are, here you have a pupil. So this anode is annular, which means it has a hole in the center. So you have a beam of electrons going in. Now this is just a schematics. You understand that the electrons can go directly, but they can go to with an angle. So you put a set of lengths, which are what they do. They focus the beam and they straighten the beam. And the next is another set of coils, which will allow you to scan the surface. And usually around the beam, you put what we call backscattered electron detection. You put another collector, which these electrons are hitting the surface and generating secondary electrons. So these are secondary electrons can be collected by the secondary electron detector. But some of the electrons are not just secondary electrons. They can be completely backscattered. So they are actually can be collected by this beam. So you can actually generate an image either of the backscattered electrons or image of the secondary electron detector. So the electron beam is produced at the top of the microscope by extraction of electrons from the filament, temperature, and/or electric field. The beam follows a vertical path through the column of the microscope. It makes its way through the electromagnetic lens, which focus and direct beam down toward the sample. And by the way, I know that you haven't dealt a lot with magnetic or electrostatic lens, but they behave very similar to optical lens. You can define focus, you can define some parameters which are equivalent to the radius of curvature of a lens. So you can actually use the lens equation even in the case of electrostatic lens. And then you put detectors. You can have a detector collecting the secondary and/or backscattered. Not all microscopes are equipped with the backscattered electron collection, but all of them are equipped with a secondary electron collection and convert them to a signal that is sent to a viewing screen producing an image. This is a more complicated structure. These are have a voltage supply to heat the filament. This is the anode, which attracts the electrons which are emitted. And here you have an aperture, which limits the beam. And then you have first lens, second lens, third lens, and then you focus it on the substrate. And when you focus on the substrate, you have electrons are hitting the substrate. They can eject secondary electrons, and some of them can be backscattered. So you can put here a sensitive, you can actually do an X-ray sensor also, because you get some X-ray from the Bremsstrahlung energy, Bremsstrahlung radiation, which is when electrons are decelerated, when they slow down. You know the rules that any charged particle, when it's accelerated, emits radiation. So also when the charged particle is stopping, you have radiation emitted. So you have X-ray emission, which can be detected, like a fingerprint. And then you can collect the secondary electrode, backscattered electrode, and then convert it to a signal and get an image. In an electron microscopy, you have few signals actually, and if you have a good system, some system can do more than just getting the image. So you have X-ray emission, and from this you can extract composition. You can have backscattered electron, and this helps you a lot looking at infrastructure, or microstructure, sorry. And then you have the secondary electrons, which also allow you to detect microstructures. By the way, the backscatters are also very sensitive to the crystalline structure, so you can use them for the crystallinity. Then you also have electrons going straight forward. This is elastically scattered electrons. This is in a TEM. So in a SEM, you look at the signal above the sample. In TEM, you have the transmitted electrons, and inelastically scattered electrons composition. So in a TEM, you look at the electrons going through the sample. In a scanning electron microscope, you look at electrons going above the sample. And you can have secondary electrons, backscattered electrons, Auger electrons, which are electrons which are emitted due Auger interaction. Auger interaction, to remind you, when an electron gives energy to another electron in the substrate, you have you can have a Auger recombination which can emit, if you excite electron to a higher level, this electron can go down to another level, to a lower level, and give the energy to another electron which is emitted. So you can have some more complicated interaction. You can just conventional secondary electrons or scattered electrons. You can have secondary electrons, backscattered, and Auger electrons, which it's a relatively weak signal, but it has very important information because they are coming from very, very close to the surface. You can have X-ray, and also some visible light, which is called, this effect is called cathodoluminescence, which in some cases you can analyze. Now, not all microscopes have all the equipment to detect it. So electron gun looks like this. This is a tungsten hairpin filament, where it's a 125 micron diameter. You pass current through this filament, and then you got emission of electrons from the tip. Or this is another very common gun, which is called lanthanum hexaboride. And the nice thing about this material, you can get very, very sharp tips. So because you have very, very sharp tips, the emission here is more monochromatic and more effective. And you take this here and you heat it up, and you have electrons are emitted. You apply a voltage between the anode and the cathode, and you accelerate the electrons. And in normal emission, they are emitted in a certain angle, and they are collected in a certain, through the aperture. And here you need to put a lens to collect them. So this is the lambda, the wavelength, h, the Planck constant, divided by 2 of the mass of the electron, q times v0, which is the potential, accelerating potential, plus the relativistic part, q squared v0 squared divided by c squared. So effect of increasing voltage in electron gun. So if you increase the voltage, and this is h divided by this number. So if you increase the voltage, you reduce lambda, which means the resolution, the penetration increases because you have more energy, but you have specimen charging increases in insulators. You can also, because now you have electrons with high energy, you can introduce damage, and the image contrast may decrease. So field emission, electron source. I'm going to say a few words about this, because if you want to get high resolution today, it's the field emission or thermal emission guns are less. We have less resolution, and the field emission guns, they have higher resolution, and it's used to generate high electric field because we use a very sharp tip. If you have a very sharp tip, if you apply voltage next to the tip, you have very high electric field. I hope you remember from electrostatics that next to a tip, the electric field is proportional to the voltage divided by the radius of the tip. So the sharper the tip, the larger the electric field. So when the electric field reaches a value of about 10 to the 7 volt per centimeter, which is 10 million volt per centimeter, then you can have an effect which is called field emission. Because the electric field is so large, basically you can detach electron from the surface, from the material. They go via tunneling and being emitted. Now, you can say to me, oh, 10 to the 7 is a huge number. But if you put like 10 volts, and the radius of curvature of your tip is 10 to the minus 6 centimeter, and 10 to the minus 6 centimeter is 10 nanometers. Now, 10 nanometers is not so. When you work today with a high resolution technology, 10 nanometer is not so small. So if you can tune your tip to be in the range of 10 to the minus 6 of centimeter, and you put 10 volts on the tip, you can have field emission. So the electrons can tunnel through. This is the tip, and this is the outer. This is kind of nice. This is a high voltage, but electrons cannot go directly outside because there's a barrier between the electrons in the material and the outside. But if you apply very strong field, then the barrier becomes narrow and narrow, and you can have tunneling of electrons via the barrier between the material and outside. And if you look at it, this is the solid, and this is the Fermi. This is the energy diagram of the solid. So normally, this is the Fermi level. Below Fermi level, all the states are occupied, so you have electrons here, and no electrons here. Above the Fermi level, all the electrons are we have states, but they are not full. And this is the vacuum energy. So in order to excite an electron from the metal to the vacuum level, we need to give it energy. So one way to give energy to the electron is to heat up. When you heat up, electrons can jump from here to here and being emitted. But what happens if you apply electric field? If you apply electric field, when you apply electric field, the potential in this direction is going down. Because electric field, and I mean when you apply a positive electric field. So positive electric field means the potential is going down. So you have to take this step and combine it with electric field which is going down. So if this is a moderate field and this is a large field, so this is the structure of, or the energy diagram next to the surface. This is the barrier. This is the potential due to the electric field, and if you apply such a high potential, we can have electrons tunneling from here to here. Because here we have possible states, and this is the barrier. And typically, you will get tunneling when this distance will be 1 to 2 nanometers. Now, since typically the work function of most metals is few electron volts, we can calculate the electric field because this is 1, 2, 3 electron volts divided by 1, 2 nanometers. Now 1 nanometer is 10 to the minus 7 of centimeter. So if this potential from here to here is few electron volts, and this potential is few nanometers, the electric field is potential divided by distance. Remember, electric field is the slope of the potential versus distance. So if you take a volt divided by nanometer, you get about 10 to the 7 volt per centimeter. So this is the electric field needed for field emission. How they look, either single crystal lab 6, tungsten wires, and field emission tip, this is how they look. And this one has a tip, this one has 100 nanometers tip. So if in 100 nanometers tip, which is 10 to the minus 5, and you want to have electric field of 10 to the 7, you have to apply about 100 volts. Because 100 volts is 10 to the 2 divided by 10 to the minus 5 is 10 to the 7, which is not so bad. It's not such a high voltage. So this is what you do to get full field emission. Now, the problem is not a problem, but you have to understand what is the mechanism of interaction between the electron beam and the substrate. This is also relevant for TEM. So what happens when the incident electron beam is scattered in the sample, both elastically and inelastically? This gives rise to various signals that we can detect. And what we have here, we have what we call interaction volumes. Electrons go inside the material, have some collisions, and lose the energy, and then this is it. So at low energy, we get this, what we call collision, or this is the collision volume, and this is a moderate voltage, and this is this is high accelerating voltage. Now, this is as a function of the voltage. Now, let's say we have the same energy, but the substrate here is a high atomic number, medium atomic number, low atomic number. So we have the electrons are actually giving me a signal not from a single point. So I can have very high, in this kind of interaction, the wavelengths of the electron can be very, very small, but the volume which is being detected can be much higher. It depends on the energy of the electrons and the mass of the atoms. And usually what we do a solid state, you can do Monte Carlo simulation. This is a electron, and by the way, there is a very nice software called by the name Casino, sense of humor of scientists. And it's a freebie, you can download it from the internet. and simulate it, but only on Windows. You cannot do it in Mac. And there's another software called SRIM, S-R-I-M, which also simulates interaction of energetic particle and solid. It's also a freebie which you can get. Or if you have funding or money, you can buy commercial tools. And these commercial tools, you shoot electrons, and then you have 1, 2, 3, 4, 5 collisions, then stops, so you can simulate the interaction of the electrons or the ions with the solid. And when you do this simulation, you find out that you have what we can call a radius of interaction. And you can look at this and define what I would call escape depth. So you have a lot of interaction here, much, much less at the outside. And some of the electrons can escape also in this direction, simply going out, completely going out. So the Auger electrons are very low. They're very low energy. And because they're very low energy, if you have an Auger electron emitted here, it does not reach the surface. So only Auger electrons from this region, Auger electrons are electrons which are emitted due to the Auger interaction. Auger interaction is when you have a high energy electron at high level going down and gives its energy to another electron which is emitted. So this typically is a low energy process. So these Auger electrons are detected for a very, very small volume. The backscattered electrons are emitted from much larger area, and the X-ray which is emitted is actually being emitted for a very large area. So if you're measuring X-ray, why do you measure X-ray? You measure X-ray because the wavelength of the X-ray depends on the material. So you can do energy dispersive analysis, which means you can measure what I have. Do I have zinc? Do I have copper? Do I have carbon? Because so carbon is a problem, it's too light. Do I have gold? Every material has an X-ray spectrum, which is like a fingerprint. So you can do a energy dispersion spectroscopy. So this is for material analysis. But you have to remember, this onion shape, you are collecting energy from large volume. So if you have a copper on silicon or etc., you can actually measure electrons from various materials. There is the special resolution of the material analysis in this technique is not so high unless you are using the Auger electrons, which are very, very high resolution, only from the surface, but very few microscopes have it. So this is what we call escape depth. The Auger electrons are escaped from the volume of 2 to 5 nanometer, and the scattered electrons, or the secondary electrons, they are emitted from a volume of 20 to 40 nanometers. And this is the backscattered electrons, and this is the X-ray volume. But a rule of thumb is that you are collecting signal from a relatively large volume. So one way to improve, to reduce the signal, is to reduce the energy. But if you reduce the energy, you increase the wavelength. So there is some limits. This is a nice simulation, real-time demonstration of a Monte Carlo simulation. This is a 5 kilo electron volt silicon. Sorry. This is a silicon and silicon. This is a tungsten. So if you're shooting 5 kilovolt electron volt silicon into silicon, this is the volume of interaction. This is 20 kilo electron volt. And this is electron into silicon. This is electron into silicon, 5 kilo electron volt 20. This is electrons into tungsten. You got much, much, much higher resolution in this case. So dependence of the interaction volume on electron beam energy and the substrate properties. And this is a simulation. Let's say this is electron beam. You see also that here electrons are emitted at a different amount than electrons here. Mouse, here and here. So what you see, you get dark, medium, and very bright. So this will give you much larger signal. So if you look at your signal, the signal depends on the mass, Depends on the energy, but also depends on the topography of the surface. So if you are looking for a silicon iron or carbon iron gold, you will get also carbon is a light material, not many electrons, so the signal will be weak. Iron is heavier and gold is much heavier, so gold has many more electrons, so you get many more secondary electrons. So you have a topography contrast and also a Z contrast, compositional. So when you see a contrast in your image, it's difficult to know if this is because of they have a different material or different topography. So be careful when you look at SEM images. Sometimes it looks so beautiful, it's a topography, but it's actually not a topography, but a difference in material. So this is images. This is the let's say defects in particles. This is nice high resolution image. This is a tilted SEM section of a scribe line. A scribe line, when you are making chips, between the chips, you have what we call scribe lines, the area where that we scribe and basically we cut. So this is a tilted SEM cross section of the scribe line, and this is the tool parts analysis. I even don't know what kind of tool it is, but this is the image of a surface of some tool analysis. Doesn't say anything. This is HDP nozzle, high density plasma nozzle, which means this is a tool that was taken from a high density plasma system, and this is it's probably made of some, I don't know. Nice, just nice. So SEM summary: signal in electron, signal out is a secondary electron or backscattered, about 2 nanometer resolution. Good depth resolution, sample size, large wafer. We can even do very large wafers. Also, the cost of the system goes exponentially with the size of the wafer. That's why in university you don't see big tools. The sample preparation is very simple. You can go out to the resolution limit. Analysis time is relatively fast. It says you 10 minutes, but some systems they have a very fast loading with a load lock, so it can be relatively fast. And pattern vs blanket, you can do both. Other applications, particle, consumable, you can do other imaging, not only on wafers. Calibration, it says here Hitachi NI standard. This is because I took this slide from Intel, which is using Hitachi tool, but you can also buy it from another company. And sensitivity is surface or Z contrast. Okay, now let's talk a little bit about focused ion beam. Now, focused ion beam is, again, it's another technology which is relatively new. I mean, it exists for a long time, but became available for, I would say, for engineers and scientists in large scale only very recently. And the idea is that and this is a focused ion beam, dual beam focused ion beam, which means it's a system that has an ion beam and electron beam. Which means you can generate a beam of electrons, you can generate a beam of ions. And the reason why people divide such system is because there is a big problem to make samples. In the good old days, what we used to do, we took the sample and break it. Simply cleave it, or try to be very careful, and then you have to polish it a little bit. But it was a completely destructive method, because once you take the wafer and break it, you cannot put it back into the fab. Also, when you break things, not always the surface is nice. Sometimes you have facets, sometimes you have, it's not always going like the way you like. So people found a much better way to make samples using ion beam, which means you can take a gallium beam. Most of the people use gallium. You take the beam, and the beam is very focused. So you can actually take the beam and cut a trench inside your sample and take a look at it. So you can, if you want to make a cross-section of a transistor, of something, you just take the beam, and inside the chip, inside your device, you cut a little bit of the surface and then take a look by the a microscope by electron microscope. So first you can do inline defect detection. You can take SEM images on wafers during process. You can do end-of-line yield, sort analysis, raster. You can do failure analysis and also imaging. This like SEM because you can, instead of using you can use the electron beam to generate the secondary electron, or using the ions to generate the secondary electrons to get two different images. All same limitations, not suitable for large areas. It's difficult to work with resists or organic materials. And this is, you have the ion beam coming from this side, and the field emission gun coming from here. So you have one beam of electron coming from here, one beam of ions coming from here, and you can cut an area and take a look at it. So this is the basic principle. The FIB uses gallium ions from a liquid metal ion source. Let me run it again. If you focus it on a certain point, what happens, you can sputter the material. If you sputter the material, you can cut the sample, and then if you can look at it from the side. If you look from here, you can see the side of the sample. So you can take an image from the side of the sample. And the gallium ions are orders of magnitude more massive than electrons. And destructive ion beam mills. It's called this kind of sputtering of removing material, because we also call it milling. So sometimes you can say people call it ion beam milling, or sometimes people call ion beam sputtering, and sometimes people call it ion beam etching. But the fact is that you take the ions and they hit the surface and break the structure, and molecules are being emitted. All these are synonyms. So destructive ion beams mills the sample surface, and secondary electrons are used for imaging. So then you can use this cross section here using the microscope part. And this is how it looks. For example, you take the focused ion beam to cut here, and then you look using the FIB for enhanced etch process. Okay, this is called. Okay, this is another thing that you can do. If let's say you want to etch this area, but you want to etch it gently. Now, one way is to do milling. Milling, you take the gallium ions and shoot them and break the material, and then you get it. Then you get sputtering. But let's say if you want to have etching. Etching is more gentle because it's a chemical process. Now, xenon fluoride or xenon difluoride or iodine are very reactive gases, and they are used to etch silicon or polysilicon or I don't know about aluminum, but maybe. The problem is that if you are using just fluorine ions, and as is, the etching rate of silicon is very, very slow. So what you're using, you take the fluorine or the xenon fluorine, and you take the beam here, you kind of eject a plume, a small amount of xenon fluoride or iodine atoms into the atmosphere. Now, when the gallium beam is going through this gas, if the molecules of the gas are kind of randomly moving by Brownian motion, when the gallium atom hits one of these atoms, it transfers the momentum, and this atom is practically changed its trajectory, and now this beam is causing this gas or iodine to move from here to the surface with a very high kinetic energy. So now, instead of having xenon fluoride or iodine ions in a very gentle mode, they are reaching the surface with very high kinetic energy perpendicular to the surface. And then this is called ion beam enhanced etching, because now we have a very, very fast etching by the fluorine ions or by the iodine ions, and this etching is only in perpendicular to the surface. So we can get a very beautiful etch by the iodine and by the fluorine, and not by the gallium. Here now the gallium is at a relative, you have to control the amount of gallium. You don't want the gallium to etch the surface. You want the fluorine to etch the surface. But the fluorine or the iodine, they get the energy or the kinetic energy from the gallium beam. So the enhanced etch rate gas injection needle is placed near the surface, and a few monolayers of either iodine or xenon are adsorbed in the surface, and the gallium ion beam is directed only onto the defined areas, milling selectively the desired material. So you can do either gallium. By the way, according to this explanation, you can also do enhanced etching, but you can also do enhanced milling, because once this material reaches the surface, the milling rate is faster. And these are the two models for enhanced etching. One is that the etching is faster because of the enhanced energy of the fluorine or the iodine. And the second one, if you have iodine adsorbed to the surface, it makes the milling of the surface much easier because it breaks some of the bonds on the surface. Either way, some people use FIB to enhanced etch processes. For example, in another option, you can deposit metal. This is, it's not so common, but people use it for deposit metal on insulator with very, very high resolution and where you want. Let's say you make a chip, and you look at the chip, and suddenly you see there is two lines are not connected. And you want to put metal connecting them. Now, you cannot do it post factum because the chip already finished the process. So what you do is, using this technique, you can deposit a very fine line, very small line of platinum on the insulator. And you can use the platinum organic metallic or tetraethyl orthosilicate compounds injected as a gas. Some platinum organometallic or tetraethyl orthosilicates are gases, and you eject them from here. They are doped to the surface, and then the gallium hits them and breaks the organometallic compound and leaves a platinum residue or a silicon residue. So what happens? Let's say you can use the focused ion beam to cut this line. Let's say this is the layout of a cell. You want to cut this line here and connect this to here. You cannot do it with a regular probe station. You are talking about lines which are less than 50 nanometers. So you cannot do it manually. So what you can do is take the focused ion beam to cut this here. And then you can use the platinum deposition to make a short here. So this is a very powerful tool in testing chips, because one of the problems with chips that after you make them, it's impossible to change them. But this technique is used to change the configuration of the chip after manufacturing to test. And this is very useful in many companies. As I told you before, let's say I want to take an image of the surface. So I take the ion beam to cut the surface. This is the focused ion beam, and then you can take the image from the side. So this is the FIB cutting, and what you do usually, you do it in angle. So you don't cut it like directly, you cut it with in an angle. So your sample is here somewhere, and this is how it looks. And now to improve contrast, so the FIB removes small amount of material, leaving a perpendicular well for imaging, same images from an angle of the previously buried features. And by the way, it's very common on top of it to coat it with platinum, just because platinum has a different atomic mass, so it gives you a good contrast in the imaging. So this is it. I had an animation here, but it's didn't work. So Fib images, this is identifying some hotspot. This is a gate cross section, and this showing a contact to gate short. This is the gate is here somewhere, and this is the contact to gate. And this is another cross section. This is extra poly that was patterned. This is the, you see this ugly shape here. So this is kind of images you find. So the Fib and the Fib together with SEM, or what we call Fib SEM. You have ions. Ions is the signal. Signal out is the secondary backscattered electrons. You can go down to 1.5 nanometer, up to 1 micron in the Z resolution. You can do it on large wafers. The sample preparation is in situ because you do the cut and then you do the image. You can do it on large wafers. Analysis time can be, say, again, 30 minutes to 8 hours. It can be sometimes much faster. And you can do it for other applications also. So this is the second part. And the third part will be combination of compositional and imaging analytical capabilities. 503. Okay. As we said before, during analysis, I can do energy dispersive X-ray spectroscopy, where what I'm doing, I'm analyzing the emission from the atoms, and usually most of the elements above boron, which is Z larger than 5. The detection limit is about 2 to 5%, so it's not so high resolution method, but it's quick, it's available. It's a poor light element sensitivity, no chemical bonding information. So it's EDS, it's very useful because it's available in the microscope. But if you want to do better analysis, you have to go to. And the basic idea of EDS is that you are looking at the X-ray emission. If you have an electron, you excite electron to another level. When this electron is jumping from this orbital to this orbital, you have X-ray emission. And the characteristic X-ray are produced by ionizing of atom by high energy electron beam, 30 keV in SEM or 200 or 300 in TEM or STEM. And practically, when you have the X-ray, you have to detect the X-ray by a special sensor, and in this specific system is I don't know if you can see the writing here, even difficult for me to see. It's a silicon, it's a lithium doped silicon, or it's a drift photoconductor. So this electron hit the sensor here, and you can detect in this kind of systems, you can show that the current that you measure is proportional to the energy of the atoms, because when the X-ray enters the lithium-doped silicon, the number of electrons which are formed depends on the number of the interactions with the silicon, which is proportional to the energy of the electrons, of the X-ray. So this is, you measure the current, which is proportional to the energy. So EDS, SEM versus TEM. So in EDS, practically bulk sample versus thin sample. If you are looking at the backscattered electrons, you are actually looking for the X-ray emitted. It's emitted for a very large area, and you are collecting. You see the electrons. You see this is your electron beam. Those are the secondary electrons which are emitted, and those are the X-ray. And the X-ray is collected from this large onion-shaped structure. So the bulk sample and there's a very large broadening, so the resolution is not so good. In TEM, you have a very thin sample. That's why the X-ray, if you measure the X-ray from in a TEM system, you get very high resolution. So EDS lateral resolution on TEM could be higher than on SEM by several orders of magnitude. So EDS is not a high resolution or not a low resolution system. It depends on the system that you're using. This is EDS examples. You can get all kind of EDS mapping. You can scan with your electron and measure the X-rays. You can do atomic mapping. And this is the image, and this is you can actually look at the various atoms. Each one you have an artificial color, and you can get very nice compositional analysis. So EDS using photon, using X-ray, sample size depends on the tool, and useful range is from carbon and above, and it's a relatively fast system, and you can do on pattern and blanket. So next one, compositional elemental analysis. Another technique which is very useful, which is using electrons, is called EELS, or electron energy loss spectroscopy. It's a very powerful technique preserving the ultimate TEM-STEM resolution and achieving a superior chemical sensitivity close to Auger electron limit. When the primary electron interacts with the specimen, it loses some energy. And then you measure this amount of energy that it loses. And the amount of energy that is lost during the interaction is proportional to the elemental composition or energy states and sample thickness. So this is electron energy loss spectroscopy. The energy loss of the primary electrons is measured by spectrometer assembled at the bottom of the TEM. So you look at the electrons going through the sample, but you compare the energy after to the energy before. So you're measuring the loss of the energy. So this is an interesting way to look at in the TEM image, because the main use is for light element detector and quantitative analysis. So you can get very nice resolution, but you are limited like in any other TEM methods. And to have a nice picture, this is the EELS system, electron energy loss spectroscopy. This is the beam, this is your sample, this is the image. You're collecting this case, you're collecting the energy in the dark field, and you analyze their mass. And by using this technique, you are practically get very nice images by looking at the electron energy loss. So the EELS STEM system is it's basically it's a complementary system to the TM. And let's move on. It's very trivial. The next one, which is I'll spend more time on this one, is the Auger electron spectroscopy, which is a surface analysis. Now, as you notice, we have some systems which are high resolution. We're going to use a beam of electrons, and some systems which are very wide area. But you can actually sometimes, you can look at electron, for example, Auger electron, you can look at very large area, or you can look for very specific areas. So you can play with this technique. So it's a surface analysis technique, and it's very useful for chemical composition and bonding. And you have an incoming electrons, they excite near surface electron, and they have some electrons emitted which are called Auger electrons, and they are emitted from very, very, very close to the surface, and they are related to the chemical analysis of the thin film. So the chemical composition, the chemical structure is affecting the Auger electrons. Even the bonding between atoms, if you have like nitrogen bonded to hydrogen, nitrogen bonded to one oxygen, when nitrogen or any atom is bonded to another atom, the electronic state depends on the atom, but also on the neighbors. So you can even observe if the nitrogen is, or the atom is connected to this atom or connected to this atom. So you can analyze also the chemical composition and also the bonding to other atoms. So this is very useful if you want to, you have a very thin layers, and you're not sure about their composition, and you're not sure about their molecular structure. So the limitations, relatively low lateral resolution. This is for a large area. and this is how it looks. You have an electron probe, so you are exciting electrons from a relatively large area, but only for a very small area are, if this is a beam coming, the Auger electrons are emitted for very, very, very small numbers, very, very small volume. So Auger spectrum of a copper nitride film, for example, this is what you see here. And this is derivative mode, which is, we don't plot the intensity, but the derivative of the intensity. But if you have a surface and you're hitting it with electrons, and you look at the energy of electrons are being emitted. So let's say you have a surface and you shoot 20 kilo electron volt electrons. So some electrons are being emitted specular, by specular emission. Some are hitting the surface, doing some interaction, and cause other electrons to come out. This is called secondary electrons. Now the electrons that can come out are due to internal transitions inside the material. Electrons going from high level to low level, causing electron to be emitted, or the electrons that you're shooting causing electron to be emitted. So if you look at the electrons being emitted as a function of their kinetic energy, and this plot is the derivative of the measurement. This is the total number of the electron is the integral of this curve. And the reason we look at derivative, because it's easier, because when you have electron between this energy and this energy, the total number of electron is like a peak. But if you take a derivative, you get a very sharp, nice signal. So one way to look at the amount of, the amount of electrons that you are collecting is a function of energy. But you don't look at this amount, you look at the derivative of the curve. This is a way that people, or analysts, prefer to look at signals. So for example, here you can see this curve like this. So it's actually, if you take the integral of this shape, it will be like a bell curve. It will be like a Gaussian, a small Gaussian. This is how spectroscopists look at this spectrum. And we know, for example, that for this specific case, if you look at this energy is for copper, this energy is the nitrogen, and this energy is for copper. So for every, if you are looking at the interaction, if electrons you have some electron interaction and you are causing electron to go down to a low level and emit electron from another level to go up here. You actually have few options. One option, electron can go down and emit X-ray. Another option, electron can go down and knock out another electron. So if you look, by the way, the probability of this effect, and this is the probability of this effect as a function of the atomic number, you can see that the probability for X-ray is going up as the atomic number is going up. The probability of Auger electron is going down. So if you want to analyze light atoms on the surface and their composition, Auger electron analysis is better than X-ray. And this is very important for organic molecules, which are, for example, containing carbon and hydrogen, which are not very low atomic weight. So if you want to analyze organic compound and contamination on the surface, Auger is a much better technique. It's very difficult to use X-ray. But if you want to analyze uranium or gold, it's better to use X-ray analysis. So this is the Auger spectroscopy, which you're looking at. You have electrons which are emitted with certain energies. And every energy is related to a certain transition between internal atoms. The internal transition between states, the internal transition of electron between states. When electron is going down, it can either generate X-ray or generate Auger electron. So the Auger electron technology, where the signal out are Auger electrons, it has a special resolution down to 1.5 nanometer, which is really nice. You can use on large wafers, no surface preparation. Analysis is relatively a few minutes to a few hours. And it's very sensitive. It can go down to 0.5%. It's relatively sensitive. It's not very sensitive, but it can go down to 0.1%. The alternative, if you want to use composition, you can do another technique where you use X-ray photoelectron spectroscopy, which means you illuminate with X-ray and you look at the emitted, X-ray photoelectron spectroscopy, you are illuminate with X-ray and you look at the energy of the emitted electrons. XPS is used to identify the elemental composition and chemical bonding of the atom near the surface. It is capable of determining elemental and chemical states composition on the top 5 to 50 angstrom. XPS sensitive to all elements except hydrogen and helium. Also, this technique can be combined with ion beam sputtering to monitor in-depth chemical composition. So let's see how it looks. XPS, in a sense, XPS is the complementary to Auger electron spectroscopy. But in the Auger, you are looking at the Auger electron. In XPS, you're just looking at the electrophoto emission. You are shooting X-ray, and you look at the emitted electron. This is classical photoelectric effect. But the energy of the emitted electrons is related to the composition of the material. So if you look at the kinetic energy of the emitted electrons is the H which is the energy of the photons which hitting the surface, minus E gap plus the work function. And you actually, what you can do, this mouse, the XPS spectrum, insensitive, intensities of the photoelectron versus the energy or the kinetic energy. And you can look, what you're doing, you can look at the energy of the emitted electron and get some information of what you have inside the material. This is how the system looks, typical system looks, and I apologize for the very small fonts. This is the X-ray hitting the surface, and electrons are emitted, and you are basically, based on the transitions, you look at the emitted electrons, you can identify what's inside the material. So this is a classical photoelectric effect, and it's very useful. And one of the reasons it's very useful is you get much higher signal than the Auger, because you can think the Auger electron spectroscopy is competitive to the XPS. By the way, SPS is sometimes called ESCA, electron spectroscopy for chemical analysis. You can, by look at the photoemitted electrons, you can study the energies or the relative energy of the atoms inside the molecules or next to the surface, which can tell you a lot about the chemical state. For example, again, if you look at, we do a lot of study of surfaces of silicon. So if you have silicon connected to oxygen or silicon connected to nitrogen, they will have a slightly different energy, because when silicon connected to oxygen, the bonding is different. So if you look at the XPS, it will be sensitive to the, not only to what atom I have, but the exact energy can tell me, is this a single atom silicon, or is this a silicon bonded to silicon, is this silicon bonded to oxygen, or et cetera, et cetera. So this is it's a composition analysis, but also give me information about the chemistry of the surface. Next technique, which even, this is really simple, SIMS. I mean, it's became very popular. One of the reasons is very simple. Second one is extremely sensitive. I mean, it's going like this. You take your substrate and you hit it with ions, and you look at the ions that you sputter, and you look at their composition. And this is it. You measure, you remove material and measure the amount of secondary ions. You remove material and measure the amount. It's a very unique analytical technique for measurement of composition and trace level impurities. It's extremely high detection sensitivity. You can go down to a sensitivity of 10 to the 16 to 10 to the 13 atoms per centimeter cube. I have to remind you that the amount of atom, I hope you remember that how many atoms you have per unit volume in silicon, per centimeter cube in silicon. How many silicon atoms we have per cubic centimeter of silicon? Do you remember the number? Approximately? Yeah, approximately 10 to the 22. If I can detect 10 to the 13, which is really amazing, but usually maybe 10 to the 16, you're talking in like a part per million. If you remember in Auger and XPS and the previous techniques in EDS, I can detect 1%, 0.1%. Seems I can go down to parts per million. So it's a much, much more sensitive technique. It depends on my etching rate and my depth resolution. Can be 2 nanometer to 100 microns. And it has very high depth resolution down to 2 nanometers. In high mass resolution, we can go, I can separate between phosphor 31 and this is a silicon phosphorus has has atomic weight of 31, and silicon H has also a mass of 31, but it's not exactly 31. One is 31 point something, another one is 31 point. So I can separate between them. The mass resolution is very high. There are two techniques that we use today. Because the atomic mass of phosphorus 31 is 30.97 something, and the mass of silicon hydrogen is 30.98. So I can detect between them. And a typical, normal SIMS system can see the difference. I need to have a reference sample. It's very critical for this measurement. I need to have a reference sample from similar. If I have an unknown composition or a new composition, I need to have something, some reference. It's destructive. I destroy the sample during the measurement, and they must sputter a large area to get a large signal and also to eliminate defects or particles. So the basic idea, I'm shooting with a sputtering material, and I look at what's going out. So I'm taking an ion, shooting it to the surface, and just see what's coming out. Of course, this is a very simple system, very simple description. The actual system is a very high vacuum system, which can cost a few $1 million. But a solid specimen is placed in vacuum and bombarded with a narrow beam of primary ions, which are sufficiently energetic to cause sputtering of the secondary ions, and I do measure the secondary ions. Now, how to measure the secondary ions? There are two techniques. One of them is called magnetic deflection. If the ions are moving in a certain velocity, and I apply a certain magnetic field, they move in a circular motion because of the magnetic force, and the radius of this motion depends on the atomic mass. So I can put here an aperture. I can collect atoms from here, ions from here, ions from here, and by just moving this aperture. And you can show this is the radius of curvature. And depends on the aperture, depends on this delta R, this will define delta M, the change of the difference in the mass I can detect. And the secondary ions are accelerated into a mass spectrometer. This is called mass or magnetic deflection mass spectrometer. And the secondary ion yield is enhanced by the right choice of the secondary ions. I can use oxygen primary or cesium primaries. This is the atomic, this is the periodic table. I can use oxygen as the sputtering ions. I can use cesium as the sputtering ions. These are typical examples for this effect. And this is a typical dose SIMS example. What we do, we sputter and measure the composition. Sputter and measure, so we can build a profile And this, for this example, is a doping or material concentration versus distance. This is boron implant for different energy. This is boron 1150 kiloelectron volt, 330, and 3000 kiloelectron volt. This is the profile of implantation into silicon. It doesn't say if it's silicon. Probably it's into a, we don't see a channeling here, so it's probably it's an angle. And by the way, this is dose mismatch, which means I take the same wafer, implant, take another wafer and implant, and measure the profile. It shows you there's some mismatch between the wafer. Questions?
This method is destructive to the material.
Yes.
So what is so good about this method as opposed to the other method?
Because it's highly sensitive. The main advantage of SIMS, I can measure doping and concentration down to the level of 10 to the 16, 10 to the 15. No other method can do it. It's destructive. You have to destroy. So you cannot do it on a product wafer. You have to do it on a dummy wafer, but it's this technique is very important for process development, I would say, and process monitoring. So you don't do it on every wafer. It's expensive. It's destructive. But you do it for, in process development, it's critical. Because in the process development, you need to know the profiles of the doping, the profiles of the materials. So, and then you don't care if you throw out the wafer, because in process development, you don't make any product wafer anyway. Yes?
Perhaps it's not that relevant, but what is the noisy area?
Sorry? What the
Noise area?
what, this one?
Yeah, is it that transition area?
Okay, this is 10 to the 14. So 10 to the 14 is probably the limit for this specific system, for this specific measurement. The limit of resolution is here, which is about 10 to the 14. So I can measure 10 to the 15, 10 to the 16, 10 to the 17, 10 to the 7 few times. So this looks like a dose of 10 to the 17 is typically threshold voltage correction. It's not source drain, or maybe well. I don't know what kind of doping. By the way, if you look here, you can see that you got one implant here and another implant. It's a kind of a complicated implant. It's not as simple. It's not just one implant. It's a very tricky way to do this kind of profiling. I don't know what's happening here in the surface. Don't ask me. This is not my wafer. But it shows you that in this system, by the way, this goes down also to 10 to the 14, which is very impressive. No other method can compare to this. So if you want to develop a new process, and you want to measure, you implant something and you want to measure it, there are two options. One option is to go to the book and trust the book. And second one, measure it once so you make sure that everything is good in your company. So this is the SIMS. You measure ions using either cesium or oxygen, and you look at the secondary ions. Spatial resolution is very gross. It's like 40 microns and more because the beam is pretty big. So it's not high resolution. Even though there are some systems which are high resolution, but it's not so common. Sample size is not so large. It's a 1 centimeter square. Not complicated to prepare. And the useful range is 1 to 2 nanometer. And it takes minutes to hours, depends on the quality of your system. And you can do it on wafer, blanket, or pads larger. What you can do, by the way, according to your comment, you can take your product wafer and do this analysis on a 40 by 40 micron somewhere out of your chip, or sacrifice one of your chips for this experiment. And then you can continue with the wafer. Now, a second method, which is also very used, is called time of flight SIMS. Let's say you are sputtering your material. This is the ion gun. It's coming, and atoms and ions are coming out. The best way to measure their mass, or another way to measure the mass, is to measure their you give them a certain energy. So if you know the energy that you give to them, you know their velocity. So if you measure their time of flight, how long it takes them to go from point A to point B, you can measure their velocity. You can measure how long it takes them to fly. So this is called time of flight SIMS. So if you have the primary ion beam impacts your surface, secondary ions are accelerated over the detector and separated. So if you have an ion with a certain mass, and you want to know the mass, what you do, you accelerate it. So if you accelerate it, you know that the velocity is acceleration times the time, and you know the final speed, which is half at squared. So if you measure the time, you can know the mass. It's a very simple measurement. It's called, in this case, you can know that the time of flight depends on the mass. So this is a very simple method. So in TOF SIMS, why do you do time of flight SIMS? It's an alternative method. With the time of flight SIMS, you can actually, there are two methods to do mass spectroscopy. One is magnetic deflection, but the magnetic deflection, you are limited to ions. You cannot do very heavy ions or very heavy molecules. If you have molecules with atomic mass of few hundreds, it's very difficult because the radius of curvature is too large. It's out of your system. So so time of flight can give you a much broader, much more molecular weight, so you can measure much heavier molecules. The resolution is comparable for the two systems, so it's a complementary system to the magnetic deflection system. So this is TOF SIMS measurement. And now, when we talk about emission, there are a few techniques. For example, X-ray fluorescence. Fluorescence is this, and I hope you remember from physics what is fluorescence. When you excite electrons to a certain level, when they go down, they emit light. This is called fluorescence. So X-ray fluorescence means you use X-ray to emit, to excite the electrons. When they go down, you measure the energy. But by the way, you can do X-ray fluorescence, which is using X-ray to excite atoms or electrons, or you can use ultraviolet fluorescence. So a few ways to do it. Now, total XRF is a technique where you take if you have a thin film and you are shooting the X-ray beam in a very shallow angle. So you are actually, when the beam is going into the film, you are below the Brewster angle. So you have total reflection inside. So which means instead of just one interaction, the beam is like going inside and you have many, many, many more interactions. So you enhance the excitation. So there are two methods which are common today. One is just regular XRF, which you can apply it for powder and for non-flat surfaces. But for flat surfaces, you can do TXRF. It's a non-destructive quantitative technique for contamination analysis on smooth surfaces. And this technique utilizes the primary beam of high energy, strikes the wafer at grazing incident angle less than 0.1 degrees. So you have to really align the surface and the beam it has to be very precise. And the atoms in the sample are excited from the top 50 to 100 angstrom level, and the characteristic energy associated with relaxation is detected using an energy dispersing spectrometer to both identify the element and measure its intensity. Sensitivity factors are then used to convert the intensity of the concentration in units. So it's said here, I put it here, about 1,000 times more sensitive than regular X-ray fluorescence. No animation here. And you can actually do the measurement and rotate the wafer, and you can actually get a mapping of contamination. And because it's extremely sensitive, one of the biggest problems in the industry, in the semiconductor industry, or in nanotechnology, microtechnology at large, is one of the problems is metal contamination. And the reason is during manufacturing, when you make devices, you use a lot of metals like tweezers, and gases are coming through metal lines, and metals, when they penetrate silicon, they can cause a lot of damage. So one way to measure metals, you need very high sensitivity methods to measure metals on surfaces, and other option is to do post-mortem to your samples, but you don't want to do it. This is a TXRF method. Another interesting technique is ICP-MS that people use in manufacturing. Is a very sensitive technique to elemental analysis and isotopic analysis of high purity liquid chemicals. All the methods I described so far were for solids, but what happens if you have liquids? So how do you cannot apply, you cannot put them in vacuum. These are liquids. So ICP-MS is a very useful technique. Practically, you are put the gas or the liquid in a vacuum system, apply some energy using, in this case, inductive coupling. You put big inductors on the side, apply RF field, and you excite the atoms. And because you excite the atoms and the molecules, they emit light, and you measure the spectrum of the light. So it's a very sensitive. You can go down to 0.01 ppb. Most elements detectable and precise quantification and small size samples. But if you have metals with high concentration of metal species inside, it's not recommended because you can contaminate your system. One of the problems, because this is a very, very sensitive method, so what happens if you put something inside that contaminates the chamber? So if you put metals inside, most likely some of the metal will stick to your chamber, and here goes a $500,000 system. So you have to be careful with metal contamination, and also isobaric, isotopes of two different elements, and you cannot, and polyatomic ion interference. You can have interference between, for example, similar molecules, or molecules of two different elements, or polyatomic ion interference. We have a good picture here. Okay, this is we took a picture of the ICP-MS that we have here. This is the chamber. You inject the gas inside the chamber. Here you put this coil. You excite the plasma. And then what you do, you are analyzing the component of the plasma, and this is the detector here. Oops. So this is, for example, what you inject this is one way to inject the material to the chamber. Sorry, this is a, sorry, I made something wrong. This one is a mass spectroscopy. Sorry, this is not a light spectroscopy. This is a mass spectroscopy. So in this case, you're generating a plasma, and you measure the mass of the species. So the mass which are being emitted, you have here a quadrupole. It's a magnetic deflection, or kind of a magnetic deflection tool to measure the mass, and this is the detector here. So this is it's not a light spectrum system. It's a mass detection system. And what you see here is argon plasma in operation. The liquid sample is introduced into the neutralizer system, where it is converted to aerosol. The aerosol is then carried into the high temperature argon plasma, which atomizes, then ionizes the sample to produce a cloud of positively charged ions. This is a quadrupole mass spec. In the initial system, I told about a magnetic mass spec. In a magnetic mass spectrometer, we have ions are coming and moving in a circle. A quadrupole is another trick. And in this trick, if you look, you see the animation here? These are, you have magnetic fields, but these magnetic fields cause the ions to move only ions with a certain mass, ions are extracted from the plasma into the vacuum system containing a quadrupole mass analyzer. It allows ions of a specific charge to mass ratio to pass through the trajectory to reach the detector. What happens here, only ions with the right charge and the right mass will go, because of the specific field, magnetic field inside, they will follow a certain path. But if the mass is too big or the mass is too low, depends on the magnetic field, of course, here. Only specific ions will reach the sensor. So this is very sensitive to ions with a specific mass and a specific charge. So this is called a quadrupole mass filter separates ions. And the signal obtained for a particular ion is compared to a calibration plot to determine the concentration for that element. So ICP-MS detection limit for various systems. This is less. This material you can get one part, 1 ppt. 1 to 10 ppt, 10 to 100 ppt. This is parts per billion. This is 10 to the minus 12. Yeah. This part per billion. This is really small. This is the 10 part per billion. This is 0.1 to 1 part per trillion. So this is kind of the sensitivity mass, and this list of components are typically measured in the fab. This is what you're looking at: aluminum, barium, boron, all this list of materials which are usually monitored in a fab. So this is example for MCP-MS. So table, now summarizing this technique. We have 5 more minutes. So what do we have today? SEM, TEM, AFM, optical microscopy. Inputs are electrons, and light. The output are electrons and light, but important is resolution. SEM is 1.5 nanometer, TEM 0.2 nanometer, maybe less, AFM 0.1 nanometer, and the light is half a micron. So light definitely is not high resolution technique. Okay, question? No question. Okay, this is typical resolution. So best for SEM is useful for all-purpose thin films, and microscopes are using for first pass analysis. You can see that today, for when we work with sub-micron analysis or nanometer scale, microscopes are not so useful. All the tools are electron beams systems, and this is a long list of the comparison between all these methods. I will not go through the list. This is summarizing the lecture. We succeeded to be 2 minutes ahead of time. So what I gave you today is 3 hours, kind of a condensed description, what people study. There's another class on materials analysis, which is given here, which is a whole semester. And they even discuss a smaller number of features. All you can remember that today in the fab, in a normal fabrication site or in a lab, there is a large availability of many tools which you can use. And you can even use various techniques to verify. For example, you can do composition analysis by XPS or by SIMS, and you have the trade-off. You can do imaging by TEM or by STEM, and you have a trade-off. You can use AFM, and you have a trade-off. So if you work in a research environment, you have to be familiar in much more details than what I described to you today. Today was like an overview of what's available. I prepared another lecture today, which I'm not going to show, is on metrology. You can keep it as a bonus if you want to do metrology. It's a kind of a secondary importance. It's not on the syllabus. We have another lecture next week. Next week, Yaakov is giving the lecture. The following week, I'm giving the final lecture on future technologies, and we'll have a rehearsal for the exam, a kind of a review for the exam. Okay? 6 o'clock, we are right in time. Thank you.